Hello, this is the final demo presentation for the Power9 Medical Imaging Analysis plugin group in the Cloud Computing class at Boston University. Our mentor was Rudolph Pinar at Boston Children's Hospital, and our team members are Nicole Elbery, Quinn Moyer, Ryan Schneider, and Aaron Thomas. We are all undergraduate computer engineering students at Boston University.
CRIS is a project produced by Boston Children's Hospital and Red Hat. It is an open-source framework that allows medical imaging analytics to utilize many different cloud technologies. It permits different health organizations to own their data while also reaping the many benefits of public computational power.
Our minimum viable product was to containerize MRI Convert application of the FreeSurfer software package to run as a CRIS plugin on PowerPC machines and to implement this into the CRIS system. To clarify, FreeSurfer is an open-source brain imaging software package, and MRI Convert is an application of this package that converts between different file formats. Our original minimum viable product consisted of containerizing all of the FreeSurfer software package. However, compiling some of these packages was beyond our scope, so we scaled it down to just compiling MRI Convert. We chose this application because it is the most widely used FreeSurfer application for target users. Like Nicole said on slide 2, CRIS is an open source framework that utilizes cloud technologies to democratize medical analytics applications and development, and to enable healthcare organizations to maintain ownership of their data while benefiting from the public cloud processing capabilities. CRIS uses Docker containers, Kubernetes, and OpenShift, as well as other technologies to standardize application development. A complete understanding of the CRIS architecture is beyond the scope of this project, but you can find more information about it at the Boston University Red Hat Collaboratory website. Currently, an instance of CRIS is already deployed over Boston Children's Hospital and the Massachusetts Open Cloud, and more medical analytics plugins are being embedded into the BCH MOC deployment, which is where our project comes in. The CRIS platform manages the control of the flow of data from a protected data source, like a hospital image database, to a remote environment like the MOC. I'll explain more how this works in the next slide. This is a system overview of how a user interacts with the CRIS architecture, and by extension, the MOC in our plugin. First, the client, such as a doctor, technician, or researcher, will upload data they want analyzed, like MRI images, and these will store in the CRIS backend, which is called Cube. The coordinator, which is called pfcon, will go into the Cube storage and compress this data. The compressed data will then travel to the data handler, pfio, where the zip file is unpacked. Sequentially, the coordinator will tell the manager, pman, the data is available and to run the necessary plugin, like MRI Convert. The data handler will give the container the data as an input directory, and the manager will tell the container, made by us, to start running. The container will run and do what it needs to do, and then send this data back to the data handler as an output directory. This data is then compressed by the data handler, and then it travels back to the coordinator through Cube, and eventually to the client. The coordinator and Cube exist in Boston Children's Hospital computing architecture, whereas the manager, data handler, and container exist in the MOC.
Alright, so I'm going to talk about what containers are and why they're useful for our project. So basically, containers make it easy to decouple your application from the environment. So in our case, what that means is that our container takes care of all the configuration that needs to be done for the CRIS app so that we can easily just deploy it to any Power9 machine. And then kind of what goes along with that is that it means that software is easier to distribute. So if someone wanted to use our MRI Convert application for Power9, they could just use our container and they wouldn't have to go through the headache that we went through of compiling it and configuring it, setting environment variables, anything like that. And then the last thing is containers versus virtual machines. So basically, what's the benefits of using a container over just using a virtual machine? And the idea is that with virtual machines, you have to virtualize and operate, like you need to virtualize an operating system for each VM that you want to run. But with a container, they can all lie on top of a shared OS, which makes it a lot more lightweight. And if you're going to have lots of containers or VMs running on the same machine, like on this Power9 machine that we're using, it's very beneficial to use containers for that because it'll just be a lot more lightweight. So as for what we've tangibly accomplished in this project, we compiled MRI convert from FreeSurfer on PowerPC, and then we created a containerized Chris plugin using that MRI convert binary, and then we also built pman and pfio on PowerPC, which are parts of the Chris system, and then we were able to communicate to pman and pfio via our own Chris instance, and we'll go into more detail about what all that means in the upcoming slides.
In order to build FreeSurfer, we first needed to build its dependencies. These dependencies are 6 packages that are built by a Python script called buildpackages.py. To build MRI Convert, our MVP, we only needed ITK. This is known as the Insight Segmentation and Registration Toolkit. This toolkit is used to identify and classify data and is commonly used for MRI scanners. To make ITK compatible with PowerPC, we had to go into its build script and remove its x86 specific flags. These x86 specific flags contain SSE, MSSE, MSSE2, and etc. These flags are used to speed up floating point operations on Intel processors. These flags are not compatible with PowerPC. So once we remove these flags, ITK was able to build properly, and then we could use it for MRI Convert. We had to use some trial and error to compile FreeSurfer to PowerPC. FreeSurfer is built using CMake. The first steps were to edit FreeSurfer's CMake build files to find FreeSurfer's dependencies by editing its CMake list.txt file. To learn how CMake works, we first installed FreeSurfer on an x86 system and edited its CMake list.txt file to find its respective FreeSurfer dependencies. With this accounted for, we needed to find where FreeSurfer made use of x86 specific code. To do this, we compiled FreeSurfer normally and looked for libraries such as SSE and SSE2. These libraries are made by Intel and they are for vector intrinsic code. These libraries are called using xmintern.h and emintern.h. We found that these libraries are included in FreeSurfer's file affine.h. By commenting out xmintern.h and emintern.h in affine.h, we allowed MRI Convert to build normally within FreeSurfer. I should mention that some other applications were able to work because of this. However, since our MVP is MRI Convert, we focus solely on getting MRI Convert working. The vast majority of the other applications did not work because they relied on more than one out of those 6 packages that I mentioned earlier.
Alright, so compiling MRI convert on PowerPC was kind of a prerequisite to creating a containerized Chris plugin with MRI convert. So what that entails is we have a Docker file which basically provides instructions for assembling our image. So things like we define environment variables, we install the necessary Python packages that we need, things like that. And then we also have some Python code that allows us to interact with the Chris system. And with the Python code, basically what we did is we defined some command line arguments that allows the user to specify what files they want to operate on, where the output should go, things like that, and then execute the MRI convert binary using those input and output paths. And then we also, of course, to execute the MRI convert binary, we embedded the binary in the image, and that's obviously compiled for PowerPC. So how we do I/O to and from the container, we use Docker volumes, which is basically persistent storage that you can mount. So you can access images from outside the container, and then you can send them back outside the container. And then kind of the process we went through to do this was we first did everything on x86 where we knew it was going to work just to get familiar with the workflow. And then we reproduced it on PowerPC. So some of the challenges we had with this was it was all of our first time using Docker. So there's definitely some learning curve associated with that. And then there's lots of subtle configuration problems. And what I mean by subtle is that things that it was pretty easy to fix once we knew what the issue was, but it wasn't so easy to figure out where the problem was coming from, things like that. So some examples of that was there is a lookup table file that didn't exist in our image that we needed to copy over. And then also something like we needed to change the entry point of our container to Python 3 instead of Bash, which in retrospect seems obvious now, but at the time we didn't even know that like setting the entry point existed, so it was hard to figure out what to do. All right, so I'm going to demo the Chris plugin now. So right now I'm on the Power9 machine, and if you look, I have this directory, input directory, which if we look at that, it just contains a bunch of image files. And then we also have a directory, output directory, and if we look in that, there's nothing in there, yeah. So I'm going to run our container now. Oops. So we have docker run, and then this is our container, plmri convert ppc64, and then we're going to mount the input directory we were just looking at to some path in the container and the output directory as well. And then this last part is the Python that we're going to run. So we're saying run mri convert ppc64.py, which is the Python file in our container that we have, and then we'll set the flag executable to mri convert. So it's basically telling it we're going to run mri convert with flag input file, the whatever file we want. So this is just one of the files in the input directory folder. And then we're going to say output file, we'll make it demoimage.nai. So our output, we're going to have it called demoimage.nai. And then these last two required arguments here are the names of the input directory and output directory. So if we run this, it'll take a little bit of time to start up the container. And then, yeah, so we see user bin mri convert, and on this file that we want in the right directory, blah, blah, blah. So mri convert's running right now. It'll take a little bit of time. Yeah, so we see writing to output slash demoimage.nai. So if we look in outputter, we have this demoimage.nai. All right, so I'm back on my local desktop now, and I'm just going to SCP over that demoimage.nai from the Power9 machine onto my local desktop. Okay, so now the Chris team has put together this nice web application that helps you view these .nai images. So we can drag this in here, and now you see it pops up over here, and we can load it, and this is the output image that our MRI convert generated, and we can view it now.
Because the manager pman and the data handler pfio of the CRIS architecture were previously only built for x86 architecture, one of our tasks was to build them for PowerPC. As mentioned on slide 5, the manager and data handler run on the MOC and not at Boston Children's Hospital, so in order to integrate our plugin with the CRIS system, we needed to build pman and pfio. We did this by first forking the existing pman and pfio repositories and making a PowerPC branch. We then had to modify the Docker files of each. This consisted of changing the from instruction to set a different base image compatible with PowerPC and adding a Python 3 installation under the run instruction, and then building these images on Power9. This process was relatively straightforward, but the biggest challenge was figuring out that the images needed to be derived from the PPC64LE Ubuntu image, as well as working around errors for Python 3 installation.
For this demo, I will be showing you a simulated CRIS backend communicating with our PFIOH and PMAN on the Power9 machines in the MOC. Here, we are looking at the inside of a PFIOH container, and over here we're looking at the inside of a PMAN container. In this section, we have an Ubuntu virtual machine, and this is simulating the CRIS backend. So now I'm going to show that we're able to send a payload from the CRIS backend to PFIOH and PMAN on the Power9 machines. As you can see, this is quite a long message. However, this message is specific to the CRIS application. So it's not that a user will sit here and type it in. This is hard-coded and will happen at the push of a button. So now to simulate a command, I'll paste it over here, and this will send to PFIOH and PMAN. So as you can see, PFIOH receives the incoming message, it parses it, then it sends the data to PMAN. In the near future, MRI Convert will be fully integrated within the CRIS client. The CRIS frontend is easy for technicians to use. This frontend is made up of a feed. A feed is a set of data that a few or several applications can be run on. MRI Convert will be instantiated and can be selected from its respective FreeSurfer application. For example, here we have an example CRIS dashboard. The technician can log in, and then they'll be greeted by this dashboard. They can select their feeds, and this is the set of data that the applications will run on. We can look at view feed details, and we are shown a graph of which applications will be run. So for here, the first one that will be run is FreeSurfer, and then we have some more medical applications. The output of these applications can be found below. To show you exactly where MRI Convert will be instantiated within this graph, we can see if we add a new node, we can see parent node, and in here, MRI Convert on the PowerPC machines for the MOC will be listed here.
Throughout this entire project, we learned crucial skills, but it also opened our eyes to many different ideas. Some skills we learned include C and C++ compilation, and the CMake process, and what goes along with it. We also learned a lot about the differences between Intel and IBM architectures. We got acquainted with Docker and containerization, which we had slim to no experience with prior to this project. Another skill we developed was creating a CRIS plugin in Python, which, again, we had slim to no experience with. Some important ideas we were introduced to include the importance of containerization. It makes it easy to ship software to users. This project allowed us to experience firsthand the difficulty of compiling and configuring software. We were also introduced to writing software that configures with a large and prior existing system, and the many challenges that come along with that. Some potential next steps for our project could be compiling and containerizing more of the FreeSurfer applications, as we only did MRI Convert this semester. We would need to build more of the packages that are required for PPC64LE, allowing for these FreeSurfer applications to be built. Another step could be deploying infrastructure to all Power9 machines by integrating the MRI Convert CRIS application with the CRIS system. It can be selected as a single node in a CRIS feed. We could also add more flagging capabilities to allow users to choose between the different architectures Power9 and x86. The bigger picture of our project is twofold. The plugin enables users to perform analytics on their data while still maintaining control of that specific data. In addition, it contributes to the decrease in hospital costs for safe and secure storage and computation, and helps healthcare organizations see the benefits of utilizing public cloud processing capabilities. This will allow hospitals to spend their finances on more medical needs and devices rather than powerful computers.